Hey guys, okay, I have not seen a single video online that talks about Maxwell's equations properly. None of them really show you the fundamentals about what each part means. So I want to do a quick video and I apologize for my setup. This is my tripod at the moment, so it's very basic, but I just couldn't let this one get away because I think, Maxwell's equations are fundamental to everything. And, Einstein even said that Maxwell's equations were part of his favorite equations. So I want to just explain the first one. And if this is helpful, let me know and I'll go into more detail on the other three. Now, I like to understand these things fundamentally. I want to know what every single bit of the equation means. You can watch a video on Maxwell's equations online and it just tells you the maths. But I'm going to try and give you a visual representation of what it means. Now, this might not be helpful, but this is how I think of these things. I go down to the most fundamental, elementary part I can. So tell me if this is helpful and if this helps you understand Maxwell's equations in your mind. So we'll do every single part, okay? So we'll start with a blank piece of paper. I haven't done this before, so I want to make sure that I write on here properly. I'm going to do it in black, so hopefully you can see that. So we're going to start with the triangle. So that is nabla. Can you see that? Yeah, you can see that. Okay. Now nabla, it looks like delta, like a change. All nabla is a differential. So what is nabla? It is basically dx, dy, dz. That's it. Okay? That's pretty bad, isn't it, for you to see? But that's all it is, right? It's d over, d over, d over. That's all nabla is. Okay, it's 3 points in space. Now, the easiest way to understand this is to put a function into each one. So for me, I think of f as a function of x equals a number, 2 or 2x. If you put f equals 2x in there, f of x, if you say x is 1, then f of x is 1, and 2x, 2 times 1 is 2. So f of x, 1 equals 2. F of 1 equals 2. I don't know, is that helpful? I hope I'm not overdoing it here. But that's the way I think of the functions, right? So to really kind of like simplify even further, this is just x, y, and z on a graph in meters. Just think of it as that way. X, y, and z on a graph. That's all you've got to do. Now, with the next one, which is called the dot product, it's just a dot like that. What the dot product means is that instead of having a comma and a comma, you have a plus. That's all the dot product means. So it means let's remove these commas and let's just have a plus. That is all the dot product means. It means just take the commas out and have a plus. So what we've got to do now is the next field is, the next symbol is E. Now the reason why I've put the arrow there is because that shows that it's a vector, it has a direction. So let's not worry about that too much now. But E means electric field. Electric field, as you know, is measured in volts per meter. Well, electric field is actually measured in volts per meter squared, but here, until we've tied it up with this, it equals volts, it's in volts per meter. So all you've got to do is put the E field into the differential equation, and now I can show you that, but I'll bore the hell out of you because you know how to do this, I'm sure. This is like super basic maths at the moment. But here's the easy thing to remember, what this side of Gauss's law, Maxwell's first equation, means. It means that we get one number because we add these together in space as an electric field in volts per meter squared. That is it. That is it. We get one number. So you might ask yourself, how can Maxwell's equations be so cool if all I do is get one number? Well, obviously you can elaborate on this. You can have, you can put it into a sequence and you can have multiple numbers. But all this gives us is one number in space on a three-dimensional coordinate system. That's it. So it's really not difficult to understand at this point, Maxwell's first equation. Okay, now this equals, I hope you can see this. Can you see that? Rho. Okay, I always do, should I do a P? It doesn't really matter. Okay, rho, P, which means charge density, divided by epsilon zero, which is, to me, one of the most famous symbols in maths. Okay, this just means charge density. So you can imagine I'm quite dense. If there was more of me in this room, the density of this room would be more. Just checking how long I've done. But most of the time people think of like electrons, like how many electrons can I fit in a certain area. Now again, this is in meters here. This charge density is in coulombs per meter cubed. So when we think of cube, just think of a cube, think of a three-dimensional cube up here, and think of it in coulombs. How many coulombs are in that meter cubed? So charge density is not difficult to conceptualize, right? It's not hard to think about something being really dense. There's more of them in that cubic meter. That's all that means. Okay, now epsilon zero is a funny one because it's so integral in maths and physics. And I've spoken to really serious mathematicians, and they say, "Oh, it's just a conversion factor." And I ask ChatGPT 100 different questions, and it gives me 100 different answers about how to think about it. But for me, this is the way to think about it. And hopefully this is helpful, but it might not be helpful for you. And imagine here we have a capacitor plate that is 1 meter. Imagine here we have a capacitor plate that is 1 meter. Imagine they are 1 meter apart. That's all you've got to do, right? We can say there's 2 ways of doing this, okay? We can either say that if you want to call it a capacitor in free space, if we put 1 volt through here, right, 1 volt, in that meter cubed of vacuum, there will be 8.85 picofarads. You could say that. You can, or 8.85 picocoulombs, whichever way, before the capacitor or after the capacitor, you can do it whichever way you want. But that's all that it means. So if we have a 1 meter plate, because when you do capacitor, you do the area of the plate, and a 1 meter plate here, and there's 1 meter between them in space, you could think of the epsilon zero, the permittivity of free space, as this stuff in here. And if you put 1 volt through there, so you could think of it as charge without the volt, but if you put 1 volt through there, you get a capacitance of 8.85 picofarads per meter. That's it. Now, there are loads of other ways to do this, right? I really like to think of it as that. When I think about epsilon zero, I think about this 1 meter cube in space, because I can understand it. I have to understand these things in my head. You could also break this up. So you could do 1 divided by 8.85 times 10 to the minus 12, which is the permittivity of free space. You could do, and you could say there's 113 billion small little voxels, let's call them, 3-dimensional pixels in this area. And each one of those pixels can hold X amount of charge, right? Or you could even say, if you were to do the charge of an electron, which is 1.6 times 10 to the minus 19. So if you were to do the number, you could say, well, each little voxel holds 1/2000th of an electron of charge. There's whatever way works for you. I won't go into this too much, just look at the time, 7.5 minutes. Whatever way works for you, I think it's so important to visualize this rather than just thinking 8.85 times 10 to the minus 12, which anyone can do. How is that really understanding, permittivity of free space? And as you know, this leads on to incredible things. If you multiply it by the permittivity, the permeability of free space, and square root it, you get the speed of light. So all kind of links back. And this is like one of the most incredible discoveries in science ever. So why not just really understand the fundamentals of this? And you'll have your own way. Hopefully you've got a better way than I have of understanding this. But that for me works. Obviously, when I do the maths, I can't always imagine that because you've got to do, using a calculator. But when you look at these really basic formulas, you want to understand that this, they call it divergence, right? But you want to understand that it's a point in space of the electric field, and it's equal to the charge density divided by the permittivity of free space. Now, you could just do charge density equals this times this. So you can work out, you can start to build a visual picture in your head that the nabla, or the divergence, the dot product, if you times that by epsilon zero, you get the charge density in coulombs per meter cubed. So there are, a lot of ways to really visualize this, and it's down to you to understand which one works best in your head. But I wanted to kind of get this off my chest because no one really talks about this. Oh, nabla is this. This is what nabla is. The dot product adds them together. E is the electric field. So you basically put the electric field back into each one of these terms. And then you've got the electric field at one point in space. And you're putting all of that into one number. You're not saying the electric field, because you've added them, you're not saying the electric field is X this point, Y this point, Z this point. You're saying it's here in this one position. And then you're saying that equals to the charge density divided by this very, very, very small number, right? Which means that if you had 1 volt here, you could say, okay, 8.85 cubic picometers. Let's not do that one. Let's just say if you were to have a very small number divided by a very small number equals to 1. So you can always go back that way. And you can say, okay, I need 1 volt to get, if I have 1 volt here, I get this tiny, tiny 8.85 picofarads of charge in here, or coulombs of charge, I should say, picofarads of capacitance in this tiny amount of space. That's how much I need to get that tiny amount. So it gives you an idea of the number. Okay, that's enough because I can waffle on. But the idea really is to explain, the basic and fundamentals of Maxwell's equations. Let me know if that was helpful, and I'll do the other 3 if you've got the will to listen to that. Thank you.